So, we have derived a formula for the propagator, as we call it. So, it is g x x prime t, which is expressed in terms of these basis functions, which are u n x and u n x prime, and it takes the system from some x to x prime at a given time t. So, as I said earlier that we can get psi of x t by solving the Schrodinger equation, time dependent Schrodinger equation, which we have written as T d S E, or we can also get it by solving or rather computing the propagator. So, what we want to show is that, or rather emphasize, is that this psi x t at a given point is the sum of contribution of coming from all the initial wave function at all possible points x prime, and that is taken into account, and the contribution from a particular point is proportional to g of x x prime t, and that is why it is called as the propagator. So, it propagates the wave function from x to x prime at a given t. Now, let us try to cast this problem in terms of the propagator, so we have to find an equation of motion for the propagator. Just like the wave function, the equation of motion is given by the time dependent Schrodinger equation, which we write it as T d S E, and we should also be able to find a corresponding equation, rather the equation of motion for the propagator. So, the way to do it is that if you go back to equation 7, where we have written the x psi of x t as an integral over g x x prime t, and psi at x prime and 0 integrated over all x prime. I will simply multiply or rather operate this psi x t by this operator, which is, so we will do it as I del del t of and minus h, that multiplied or rather operated upon psi x t will allow me to write I del del t minus h, and there is a g x x prime t, and there is a psi x prime 0, and there is a d x prime. So, this tells me that this will act, this operator here will act on this function, which is g x x prime t psi of x prime 0, and this operator will actually act on the psi of x prime 0 and will give me an equation which is equal to I del del t minus h g x x prime t equal to 0. So, once again to iterate that in order to find out the equation of motion for the propagator, which is g x x prime t, I have taken this operator I h cross del del t minus h and operated on this psi, which is basically the time dependent Schrodinger equation, and that is put here, and since that is equal to 0, we get this equation, which is I del del t. There could be a h cross, which is inadvertently I have missed that, it could be there is a I h cross del del t minus h acting on the g x x prime t is equal to 0. So, let us call this as equation 9 and this as equation 10. So, this is the Schrodinger equation for the propagator. So, so far we have not done much, excepting that we have written down the time dependent Schrodinger equation in terms of the propagator. And one sort of similarity is very apparent, is that in this problem we are trying to cast the G, the propagator, with the same role that it has in ordinary quantum mechanics, and the reason we want to do would be apparent later, or rather understood later, in which we will connect this propagator with the Green's function, and this Green's function will help us in formulating a number of things, or rather compute a number of experimentally observed quantities in terms of the Green's function. So, here we may like to actually talk about specifically t greater than 0. So, what I mean is that this t that appears in your all these slides is only greater than 0. So, what happens to the wave function or the propagator as you move backward in time is not discussed, or rather it will be discussed in a more general sense, but right now we want to concentrate on the fact that I only evolve a system positive in time. So, that t is greater than 0, in which case I would define a propagator called as the retarded propagator, and this propagator is written with a g r with the same indices as we have for g. So, a g r is defined as x prime t, which is equal to a g x prime t, and a theta function. I will tell you the meaning of the theta function. So, this is equation number 11, where this theta function is defined as it's equal to 1 for t greater than 0, it's equal to 0 for t less than 0. And this is also called as the step function, or it also has a name which is called as a Heaviside step function. And so, this immediately makes it clear that g x prime t exists for all time, positive and negative. However, g r which is also a function of x prime and t exists or non-zero only for t greater than 0, and for t less than 0 it vanishes because of this theta function, the way it is defined here. So, this is my definition of g r. So, it is very clear that g r makes a discontinuous jump from 0 from t equal to 0 to a finite value. So, now the job of course is trivial to find out a Schrodinger equation for g r. We have already found one for g, Now, we will have to find the same thing for GR, which is called as a retarded propagator. So, that is the job at hand. So, I need to do a time derivative, a partial time derivative on the g x x prime t and theta t, more like a chain rule that we have for the derivatives for equation 1. So, let us see how one does that. So, I have I h cross del del t of g r x x prime t. I am only looking at the time derivative, and that keeping theta function as constant, I simply do that for the g. And now, keeping the g constant, I have to do the same on the theta function. Now, what is the derivative, time derivative of a theta function? That can be easily understood if I plot this figure to actually graphically represent a theta function. So, this is so this would be it is rather 1 minus theta function that I have drawn as a function of t, and a theta function would look like theta of t versus t, and it looks like, so this is t equal to 0. Okay. So, this is my theta function, and I have to take a derivative of the theta function. Look, this function is 0 for t less than 0 anyway. This function is equal to 1. So, this value is 1. So, this value is 1 as well, and this value is constant for all t greater than t equal to 0, and it only has a discontinuity at t equal to 0. So, the derivative of the theta function is actually a delta function. So, which is a d dt or a del del t if you write it more correctly. So, this is the definition of the time derivative of the theta function. So, I will simply get a derivative, so a delta function here, which is a derivative of the theta function. Now, this, if I recall the Schrodinger equation that we have written down for g, it becomes automatically I h cross del del t of g r x x prime t. This is equal to a theta function and multiplied by a h and a g x x prime t plus I h cross g x x prime. Now, in order to have a delta t being multiplied with it, we need to, this would only be non-zero, a delta function is only non-zero at t equal to 0. In fact, it is infinite for t equal to 0, and at all other t it is 0. So, a delta function really looks like an infinite discontinuity at t equal to 0. So, thus it makes sense that there is an infinite slope for the theta function at this point that is shown here. So, this, so to have t equal to 0, I will simply write this as, so g x x prime 0. So, my equation for the Green's function, the retarded the retarded propagator, which is what we were calling it, is this, and if I rearrange this, if I bring it to the other side, I will simply have I h cross del del t minus a h, and now acting on the g x x prime t, this is equal to a I h cross a delta x minus x prime and a delta t. Okay. So, this is just written notationally, because that will be this is by if you go back, then we have done this, that the actually this Green's function from equation 8, or rather the propagator in equation 8 could actually be written as delta of x minus x prime, and that is the delta function in time. So, this is my Schrodinger equation for the retarded propagator. So, I will use a slightly shorthand notation for the Schrodinger equation for retarded propagator. So, this equation is what we need to solve for if we need to know the retarded propagator, and this propagator needs to be computed for a given problem in order to know the time evolution of the wave function for that problem. And this is going to be an important equation for our analysis just in a while. So, now let us look at that how we can connect this to a physically meaningful quantity such as a g x x prime omega. See, omega is the energy variable, rather it is the h cross omega is the energy. So, this is a energy variable that is written as this is the energy variable, and with just the h cross added to it, it becomes a energy a dimension of energy. And since it's conjugate to time, so omega is conjugate to time. In fact, the response of the system is often expressed in terms of g x x prime omega, which is at a given omega value, or rather energy value, one can compute the propagator. So, we can write a g r here, because this is what we are interested in, and for getting this we will have to do an integral of the form which is x x prime t, which exponential I omega t, or one can write it. So, this is E over h cross, then or you can write it as E over h cross into t, and then you have to integrate over this. So, basically this tells you that there is a Fourier transform of g r x x prime t is being taken. Now, remember that this has a form which is like u n of x prime. Let me just make sure that I use the same notation. So, it is u n x and u n star x prime. It is u n x and a u n star x prime exponential minus I e n t over h cross, and if I so there is a sum over n, and if I use it there, then I will have an integral of the form which is exponential I could be h cross omega minus E n t by h cross and d t, and from 0 to infinity. We are not going to minus infinity, because we are using the retarded propagator, which is only valid for all times t greater than 0, in which case we will have to solve this integral, and this integral diverges as time goes to infinity. So, this divergence is removed by a trivial factor by introducing a small complex damping into this equation. This will be done over and over again. So, I will simply do it mathematically here. So, I will take a small imaginary part here, and I will write it with a plus I eta for the moment, and this integral is convergent. So, in physics we do not want to deal with divergent integrals, and because this integral is it diverges as t goes to infinity, we need to put a damping factor. Ideally, a plus and minus damping both would have been fine. In this particular case, we would discuss it with a plus sign, and I will tell you the reason that we are taking a plus sign here. And then my g x x prime omega, it simply becomes, I am skipping one step which you should fill it up, and this is equal to a u n x, a u n x prime. You can write it with a notation that we have used, and there is a divided by h cross omega minus E n and a plus I eta, where actually eta goes to 0 in the limiting case, in the limit. So, this would be my equation, maybe this is my equation 12, and this I will write it as equation 13. So, this is my propagator, rather the retarded propagator, I should put a r there, a retarded propagator written in the x omega space, that is the this variables are kept, the space variables are kept intact, and the time variable has been Fourier transformed into the energy, and we write it as a function of omega. If you further want to get rid of this x and x prime variables in favor of the momentum variables, one should write it with g r and a k omega, where k would be a momentum vector connecting the points x and x prime. Now, what is the relationship between so the relationship between propagator and Green's function? I have used it a couple of times, but in those all these situations we actually meant the propagator. This g also represents a Green's function. Right now we are talking about Green's function in quantum mechanics, or rather in a single particle description, but we will also talk about many particle Green's function in our subsequent discussion. So, this Green's function is defined as this g plus is the Green's function, and this Green's function, I will tell you what the plus means. This is equal to 0 to infinity g r x x prime t exponential I h cross omega plus I, sorry, this will be just a plus I eta t and dt. So, G plus is called as the retarded Green's function, and we will take a specific example to compute retarded Green's function, say for the free particle or for that matter any case. So, again the Schrodinger equation for the retarded Green's function would simply be equal to minus h minus h cross omega minus I eta acting on a G plus and omega. This is equal to a I h cross delta x minus x prime, and this is our equation for the retarded Green's function. So, we this is the equation or rather the equation of motion for the retarded Green's function, and it is also of importance to calculate G plus x x prime t, in which case you need to do a Fourier transform of G plus x x prime omega. Now, that would involve an integral of the form which is exponential minus I omega t divided by h cross omega minus E n plus I eta and d omega. Now, this integral can be thought of, or rather in order to compute this integral, one can think of omega to be a complex variable Now, this limit of omega actually goes from minus infinity to plus infinity. Okay. So, one really has omega going from minus infinity to plus infinity on a real line. However, because of this I eta, one can think of omega to be a complex variable, and there is a pole. If you are conversant with complex integrals, there is a pole at E n minus I eta, which means that it is in the lower half of the complex plane, because your eta is a positive number, an infinitesimal small positive number. So, we will have a pole at omega equal to E n over h cross and a minus I eta. It should be also divided by h cross, let us call it then eta prime, where eta prime equal to eta over h cross, and so it is in the lower half plane. So, it makes sense to actually do this complex integration by closing the contour from below and closing it like this in a clockwise sense, and call this thing as the gamma, the contour to be gamma. So, what I do is that in order to do this integral from minus infinity to plus infinity, I convert this into a closed integral over this entire loop that is shown, and I will subtract out the curved portion from that, so that I get what I actually want. This is the first term, which is a closed loop integral, can be found out from the Cauchy's formula, and which is the 2 pi I into sum of residues, and the second term will vanish because of the Jordan's lemma. So, I will write that briefly. So, this from the Cauchy's formula, and this one vanishes because of Jordan's lemma. So, in which case what one gets is that, let us call this integral to be of. So, this involves an integral, let us call that integral as I n. So, this I n, if you use this prescription that I have shown, one gets it as 2 pi I into the sum of residues, which is E n minus I eta t over h cross. This is of course, for t greater than 0, and this integral is equal to 0 for t less than 0. Now, to get back to our retarded issue, had we added a minus I eta in this expression in order to make it a convergent integral, in which case we had to actually talk about only t less than 0, which is called as the advanced propagator, which would have given rise to an advanced Green's function. So, right now we are talking about retarded propagator, because most of our physical problems or the physical observables are related to the retarded Green's function. So, then my G R, which is the retarded propagator, is related to the retarded Green's function, which I have written it with a positive sign, is exponential minus I omega t d omega, and which is nothing but 1 over 2 pi h sum over n u n x and a u n star x prime, and this is multiplied by this I n, and this is my either you call it a so this is how to get my retarded propagator or the retarded Green's function for this problem, where my G R is the retarded propagator and G plus is the retarded Green's function. So, this is in contrast with my advanced propagator, which we will call it as G A as the advanced propagator, and so G minus is my advanced Green's function. And in the next, we will give an example how to calculate this propagator for a given problem. Just once again to remind you that instead of solving a differential equation given by the Schrodinger equation, you can solve an integral equation for the propagator or the Green's function to have the same amount of information that is available by solving psi from the time dependent Schrodinger equation.